Okay, good morning, everyone. Welcome back. Orientation, as always. Undergrads, you will be submitting A5 tonight if you haven't done so already, and moving on to A6. And graduate students, for those taking the course for graduate credit, when you submit 9 and 10 tonight, congratulations, you've reached not the end, but the end of the beginning. So for the graduate students, as promised, you are now going to be entering on to an additional set of weekly programming exercises in which you're going to do everything again: links, joints, sensors, motors, neurons, and synapses. But you're going to be redoing all of those 6 items inside of a differentiable simulator. The reason why you will be doing it inside a differentiable simulator means you will be able to throw away the evolutionary algorithm and replace it with a different optimization process called gradient descent. Remember our discussion about evolutionary algorithms? They're super simple, but that simplicity comes at a cost. What's the cost? What's the drawback of an evolutionary algorithm?
You can't tell if you found like the global maximum. You can only get to local. Maybe it's the global, but maybe it's not.
You never know whether you've reached the optimal or not. Bad news, that's also true for gradient descent. Also a problem. What's the other problem with evolutionary algorithms?
Efficient, like stepping generations.
They're inefficient, right? So we're searching a space through random mutations. What a surprise. Most random changes make things worse rather than better. If I opened up your laptop and randomly started to move some bits around, I doubt I'm going to make your laptop any better. Probably going to make it worse. The advantage of gradient descent, on which the whole edifice of modern AI is built, is the concept of gradient descent. We're going to go through it very, very briefly now. I'm going to do a 3-minute summary, and then down in lecture 22, where we're going to talk about differentiable robots, we'll go through robots combined with gradient descent in more detail. But just for the benefit of the grad students that are starting on the first of 5 differentiable assignments today, here we go. Let's take our familiar hypothetical 2D, 2-legged robot with 2 joints, 2 motors associated with those joints. And let's assume for the moment we have a sensor that we're going to call X that measures the horizontal displacement of the robot. It's kind of a magic sensor, doesn't really have a direct analog in reality, but just to keep things very, very simple this morning, let's assume we have a sensor neuron called X, and that sensor neuron may connect to some other hidden neurons, H1 and H2, for example, and H1 and H2 connect to the motor neurons, and so on. So we've got our little brain inside our hypothetical robot. Let's imagine this robot operating in a differentiable simulator, which is very much like PyBullet or any other physics engine, in which we're going to start. Step 1, we're going to start by polling the sensor. What is the current value of the sensor? Let's assume the current value of the sensor is at x equals 0. 0 goes in here. The value of the sensor neuron flows down or propagates down into the hidden neurons, as we talked about in our discussion of neural networks. And then finally, the values of the hidden neurons propagate down to the motor neurons and ultimately down to the motors that control the joints. Step 3, sense, think, act. The sense, think, act cycle that we often talk about in robotics. Now there are forces acting at the joints. The physics engine takes over, does a little bit of F equals ma, force equals mass times acceleration, and uses that to compute the new position of the robot at the next time step. Yeah? Okay, around and around and around we go. Assume that our fitness function, as always, is to get our robot to move forward, or in this case, move to the right, maximize X. At the end of the simulation, we can compute the fitness of the robot, how far it travels to the right. Now the first difference is going to come in from everything you've heard so far to differentiable robots. Instead of computing fitness, we're going to compute behavioral loss. So The loss is the term that's often used in machine learning to represent error or inefficiency. Here, it represents the inefficiency in the behavior. How poorly did it do at moving to the right? We could compute this as there's a particular value of x that we want the robot to get to, and if it gets there, behavioral loss equals 0. If it gets close to there, behavioral loss is close to 0. If the robot stays here, or God forbid moves backwards, behavioral loss is very high. So in our differentiable simulator, we're going to try and minimize behavioral loss. Usually when we're talking about an evolutionary algorithm, we're trying to maximize fitness. So far, so good? Okay, so step 4 is we compute behavioral loss. How bad did the robot do at whatever we want it to do? And in the differentiable simulator, we have now completed what's known in machine learning as the forward pass. The forward usually refers to forward from the input layer of our neural network through to the hidden layer and out to the output layer in traditional neural networks. Similar here, we're also moving forward from the input neurons to the hidden neurons to the output neurons, but we're continuing the forward pass into the physics of the robot, into F equals ma, and into computing behavioral loss. What is the horizontal position of the robot? I'm skipping over some of the math. We'll come back, we'll do the complete math in lecture 22. So far, so good? So the robot sense, thinks, acts, alters how it moves, alters its ultimate horizontal position, affects behavioral loss. And now we've finished the simulation. Simulation is turned off. And now we start the backward pass. The backward pass is orchestrated or run by gradient descent, which is the new optimizer that we're using. What does gradient descent do? Gradient descent starts, step 5 here where we left off, it starts with behavioral loss and works backwards, runs everything in reverse. So where do we go? We go to the motors. Here. What were the forces at the motors that caused the robot to move in such a way that it suffered this behavioral loss? In essence, what the backward pass does is it assigns blame. So the robot had some inefficiency. It didn't move as far to the right as we wanted. Who's to blame for that behavioral inefficiency or that behavioral loss? The backward pass is going to work backwards through the body and brain of the robot and assign blame as we go. So far, so good? Okay. So we're working backwards to step 3 here, and the forces that acted on the joints, the gradient descent looks at them and says, the force at this point was this much newtons of torque, this much rotational force. There should have been a little bit less force here, a little bit more force here. At the previous time step, there should have been more force here and less force here. Gradient descent is, when done right, is all-seeing. It can see everything and knows exactly who and when, who, what, where an error occurred. So there are ways in which we could change the forces. Gradient descent tells us these are what the forces should be, and we can keep going backwards. So we've just come in the backward pass, we've come to step 6 here. We can keep going backwards into the synapses that led into the motor neuron, and we can start to assign blame to the synaptic weights as well. Now gradient descent is saying there was too much force here, we wanted less force here, so in order to get the less force here that we wanted, we should decrease the value of this synaptic weight, for example. There was too little force here, there should have been more force here. Continuing backwards, gradient descent says in order to get the forces here that we should have gotten, we should change this synaptic weight by this amount. So you can visualize the backward pass as moving backwards through the robot, assigning blame and altering things a little bit, changing the synaptic weights here. it continues backwards into the hidden layer and says the values of the hidden layers that when multiplied by the old synaptic weights gave us the bad forces that gave us the high behavioral loss. So I'm also going to assign blame to the hidden neurons. The value was this, it should have been that. We keep going backwards through the synapses that connect the hidden neurons to the input neurons and assign more blame there, and also assign small changes to the synaptic weights. And we get all the way back to where we started at step 10, the input value of the sensor neuron, and gradient descent says, I don't know how to change that number because that number is just coming from the physical simulator. I'm done. Okay. Make sense? We flowed forward in the way that we talked about when we discussed physical simulation and neural networks, and then we flowed backwards from the behavior of the robot into its brain and assigned blame as we went. Gradient descent, unlike an evolutionary algorithm, does not play with dice. There's no randomness involved, so it's much more efficient in how it does things. If you get all of this right in assignments D1 through D5, it's guaranteed that when you now execute a second forward pass with slightly altered synaptic weights, gradient descent guarantees you that at the end of that second simulation, behavioral loss will be closer to zero. It's going to reduce, it's guaranteed to reduce loss. What does that mean for us, where behavioral loss was how little it traveled to the right? It means at the end of that second simulation, the robot is going to move further to the right. Questions? So far, so good? Okay. Everything should look more or less familiar if you've taken a machine learning class. We're propagating error backwards and we're changing synaptic weights. Here's the fun part from the robotics perspective. Remember that behavior is a result not just of the weights of the synapses, not just based on features of the brain of the robot, but also features of the body of the robot. So what you'll find in D1 through D5, when you implement the backward pass, you can set up the backward pass to not just alter synaptic weights, but to alter parts of the body. Perhaps gradient descent says the weight of the front leg, the mass of the front leg, remember F equals ma, M stands for mass, the mass is also to blame for a non-zero behavioral loss. The differentiable simulator will allow you to know, or will allow gradient descent to tell you if the mass of this leg had been a little bit less or a little bit more, the robot, given all of these synaptic weights and given this brain, would have traveled further to the right. So the backward pass, when you do the differentiable assignments, you can set it up so that it also makes changes to the body, not just the brain. It can non-randomly optimize or improve the physical structure of the robot along with the synaptic weights, and guarantee you that the next time you do the forward pass, the robot's going to travel further to the right. Okay, that's a crash course on combining gradient descent and robotics. If you didn't follow all of that, it's okay. We'll come back to it in lecture 22. Lecture 22 is almost the last lecture in the class. What I just described is the bleeding edge. This is as far as we've gotten in this branch of robotics. Sounds easy. It's not easy to get all of this to work correctly, to put all these pieces together so that it works. It's an area of active research in my lab and other labs. We'll talk about it later, towards the end of the semester. But that should be enough for the students that are tackling the differentiable assignments. Questions? Okay, all right. Back to where we were. We are going to finish up lecture 9 over the next few minutes. We're going to conclude our discussion of minimal cognition. These are some old experiments now, 26 years old, that laid the groundwork for a particular approach to creating intelligent and safe machines. Strip away as much complexity as you can and see whether you can get an optimizer, either gradient descent or an evolutionary algorithm, to gradually embody the building blocks of intelligence into that machine. How far can you go? We'll spend most of our time this morning on lecture 10, where we're going to and conclude our segment on the early history of evolutionary robotics. And we're going to tackle a fifth building block of intelligence called active categorical perception. This is something you spent a lot of time doing in the first months and years of your life. We'll talk about it shortly. Okay, so back to minimal cognition. Remember that in the minimal cognition lecture, we were looking at sort of the Robo-Olympics, 4 different building blocks, and we were seeing how the investigators embodied or evolved those building blocks of intelligence into very simple robots. I introduced last time the 4th of these events, known as selective attention. Of the 4, this is the one that's most challenging. It's also challenging for us humans. There are many things going on in your world, some of which, many things in your future, some of which you can see literally and some you can't see, and you spend a considerable amount of your brain power thinking about those different events in the future and which one to take care of first. You may be taking this class because you hope it increases your job prospects. You're hoping to tackle or get a good job in the future. You're attending to that task right now by being here in lecture and listening to me. There are other things that are important to you in the future. You've chosen, hopefully, over the next 60 minutes or so to set them aside, focus on this, and then after class, you might select to attend to some of those other things in your future. Okay, so how do we strip this down to a minimal version? We're back to our little Space Invader robot that's moving left and right along the bottom of the screen. It's armed with a CTRN. 2 of the neurons inside that CTRN are controlling the 2 rockets that push it left and right along the bottom of the screen. Another 7 neurons inside that CTRN. 1, 2, 3, 4, 5, 6, 7, 9, 7, 9, doesn't matter. 9 of these neurons have been attached to proximity sensors, which we've seen before. The robot can move and sense at the same time. The investigators are then going to drop 2 independently moving objects from the top of the screen that are going to fall at different speeds, represented by the magnitude of these dashed arrows, and they're going to fall at different directions, represented by the directions of these arrows. When they drop the 2 objects at the top of the screen, sometimes they're going to put one at a lower initial height so that it's initially closer to the agent than the other one. And the goal of the robot is to quote unquote catch each object when it hits the ground. So performance of the robot, as always, is going to be an average over its performance in the ith trial of num trials. P sub I, the performance of the ith trial for a given CTRN, is the sum of the distances. What was the horizontal distance between the agent and the object when that object's final position, when it hit the ground? P sub I is sitting to the right of a minus sign, which is a reminder that in the fitness function, we're trying to minimize this term. We're trying to minimize P sub I, we're trying to minimize the distance between the robot and where the object hits. All good? Okay. Why is this task more difficult than the other 3 we saw last time?
It's managing 2 objects at once instead of just one thing it has to focus on.
It's managing 2 objects at once. It's got to select to attend to one or the other depending on what's going on. Can we be more specific? From the robot's perspective, armed with these 9 proximity sensors and the ability to move left and right, why is this hard?
Because it has to determine the goal itself. That it doesn't have the goal given to you. It has to determine the goal.
Good point. That's been true of most of the evolutionary robotics experiments we've seen so far. The robot doesn't actually know what it's supposed to do, or the CTRN that's sitting inside the robot doesn't know what the goal is. But CTRNs that score low against the goal are deleted, and the CTRNs that cause the robot to do a better job at the goal survive and reproduce. So not knowing what your goal is doesn't necessarily make things hard on the robot. I don't know what my goal in life is. I don't know if you know what your goal in life is, but we seem to get along more or less okay.
It needs to calculate like which object is going to hit first and leave enough time for it to actually move there.
Which one is imminent? Which is the one that's going to hit first, and how to get there. So we're already starting to take this difficult task. It's difficult to select what to attend to, and we're breaking it down now into sub-problems. There's different ways you can break down these sub-problems. The investigators pointed out from the point of view of the robot, there are two. There's the passing objects problem. It may be that the object that is initially further away from the agent is falling faster and therefore is going to hit first. So the agent has to possibly figure that out sooner rather than later, so it has enough time in this cartoon example to move to the right and capture the one that's initially further away, but it's going to pass this object and hit first. So this agent, or this CTRNN inside this agent, has to reason about, think about things that are happening and in the future. Which one is going to hit the ground in the future? This robot is going to be capable of prospection. Introspection, looking or thinking within. Prospection, thinking into the future. What's going to happen in the future? Prospection. Okay. The other second subproblem that the robot needs to solve is the object permanence problem. It's got to, quote unquote, look at both objects and compare their speeds and then figure out which direction to go. And possibly as it goes chasing after one of these objects, it's going to lose sight of the other one. Its cone of perception is going to pass beyond one of these objects, and the robot is going to, quote unquote, have to remember where that object was, which direction it was falling, how fast. There's a lot that this robot, or this CTRNN, is going to have to mentally juggle. Okay, difficult task, but not impossible. David Buckingham, who took this class several years ago now, did this as a final project. He recreated this experiment in the physics engine that we were using at that time. This is the most fit evolved CTRNN that David was able to evolve. Hopefully from this video you get a sense of why this is difficult, and you should see examples of the object permanence problem occurring and being solved by the robot, and also instances of the object passing problem and being solved. In some of the trials you're watching here, there is no object permanence problem and no object passing problem. In other trials, one of the two problems is at hand for the robot. And in other trials, the robot has to deal with both problems. Both problems exist. Okay, so what we're going to look at to finish up this lecture is, as always, Fitz.
I'm just curious, like, why 200? Like, what, why not 300? Where does that kind of intuition about
Yes.
this sort of quote-unquote magic number come from?
This magic number, I don't know if they mentioned in the paper. My guess is that the worst thing this robot can do is be as far from every object when it hits the ground, and that's probably an average of 200 length units. They were probably trying to normalize this overall equation to get values between 0, where the right-hand term would be 200. That's the worst you can possibly do, up to a maximum, which presumably is 200. 200 minus 0 is kind of the best you could do. That's my guess, but have a look at the paper. Okay, so as always, evolve, and evolve populations of CTRNNs. At the end, they take or they extract from the evolved population the CTRNN with evolved parameters that does the best job, gets the highest fitness. And they're going to play back that evolved CTRNN 5 times 5 new trials, and these trials are organized from easy through medium up to most difficult. So let's start with trial number 1. They're playing back an evolved C tier and N. The investigators dropped the object pair in such a way to make things easier on the evolved C tier and N. There was no passing objects problem and no object permanence problem. Okay. As always, we've got these weird cryptic figures which actually communicate quite a bit of information about the evolved behavior of the robot when it's armed with this C tier and N. What does the squiggly black trajectory represent, do you think?
Is that the movement of the robot?
It's the movement of the robot. Remember, the robot moves horizontally back and forth along the bottom of the screen, and time is elapsing as we go from the top to the bottom of this figure. So for the first half of this simulation, the robot is going left and right, more or less where it started, and then it starts to jag to the right for the second half of the simulation. That's what the jagged trajectory is telling us. What do the 2 straight black lines represent?
Trajectory of the falling balls.
The trajectory of the 2 falling objects. What do the 2 shaded polygons represent? A little trickier. Given the movement of the trajectory, we know that horizontal position within the figure represents something horizontal in the simulation. And the vertical height of these polygons represents something to do with time.
Is it like the cone or the field of view where if you're within that trapezoid, you're able to see that object, and if you're outside of it, then you're not able to?
Exactly. And thank you. These are trapezoids. I always forget. Rhombus, parallelogram, trapezoids. The 2 trapezoids. The robot starts at the midpoint, the horizontal midpoint at the beginning of the simulation. That's where the trajectory sits. And it's sitting within the lighter trapezoid, which means it can see this particular object. You'll notice that the trapezoid starts pretty wide, which means as that object starts to fall, the robot can be this far to the left and this far to the right, and it would still be able to see this object. If the robot moves too far to the left out into the white or outside of the lighter trapezoid, it can no longer see the object. The width of the trapezoid is getting narrower as time progresses. Why? The horizontal range that the robot should be in to be able to see the robot is narrowing as time moves forward.
The sensors for vision originate from the agent, and there's the inverse square law, right? That the further you get, the more light spreads out.
Yes, so that's kind of approximated by the way they've put these proximity sensors on the front of the robot. But the cone of perception near the robot is obviously narrower, and as the object gets closer, it's easier for this narrow neck of perception to pass outside of the objects. When the object is up here, obviously the spread of perception is much broader. It's easier for the robot to see the object. There's more positions the robot can have where it sees the object. So kind of counterintuitively for us, given our visual systems, the closer the object gets to the bottom of the screen, the quote-unquote harder it is for the robot to see it. Or the more work the robot has to do, has to figure out where to be to see the object. You'll notice that the janky trajectory here is actually sitting within the lighter trapezoid and the darker trapezoid. What does that mean? What does it mean when the jagged trajectory is within both polygons? What is that telling us? Yes? It can see them both. Exactly. So the robot starts here and basically moves back and forth, but it's staying in the same position. As always, this highly fit CTRNN is sort of causing the robot to show off. It's staying right underneath the object that's going to hit the ground first. What happens the moment that robot successfully captures the first object?
It moves immediately over to where the next object is going to be.
It immediately moves over, and you'll notice that it's already within the darker trapezoid, so it can still see the second object. There's no object permanence problem here. And again, it's showing off. You can see the robot moving back and forth where directly underneath the object, and then has plenty of time to capture it. So far, so good? Okay. 1 out of 5 so far. Let's move on to a second trial that's a little bit more difficult. In this case, there's the passing objects problem. The object that is initially further away from the robot is falling faster. So as both objects fall, at some point, that faster moving object is now going to be closer to the agent and hit the ground first. What does the dashed horizontal line represent, do you think? I just gave you a very strong hint.
Is that the point at which the objects pass?
So this is the point in time in which the objects pass one another. What does this evolved CTRNN cause the robot to do in this case?
It kind of stays in, it doesn't commit to one until it knows which one is going to hit first.
Commit to one. It doesn't commit to one until, I don't know, after the passing of the two objects. It looks as if the robot maybe doesn't know, quote unquote, or is trying to decide, quote unquote. Who knows? All we know from its behavior, it's sort of passing the Turing test here by acting in a way that most organisms would act under these conditions. There's two situations that are going to become relevant to the agent in the future, and it's looking at both of them, comparing them, weighing its options, and then at some point it starts to quote unquote commit to the correct one. It moves towards where the first object is going to hit, and then goes back to showing off by immediately moving towards the other slower moving object and is there in plenty of time to catch it. 2 out of 2 so far. Not bad. We're batting 1,000. All right. Trial number 2 is the converse. No more passing objects problem, but the objects are now falling at very different angles and actually moving away from one another horizontally, which makes things hard for the robot. How? You can see it from the figure. How is this situation more difficult for this CTRNN?
Needs to catch the first one and then move really quickly to the left to grab the next one.
Okay, so it caught the first of the two objects. Great. What's the situation from the perspective of the agent at this moment in time?
It loses sight of the second object.
It's lost sight of the second object. It's outside of the darker trapezoid. It cannot see it. It immediately starts heading to the left, which shows us behaviorally that the robot, quote unquote, knows where the object is, or at least knows on which side it is. It might be moving to the left saying, I know the second object is over here somewhere. I'll just keep moving until, oh, there it is. Now I'll track it as it falls. Alternatively, the CTRNN might actually know quite a bit of detailed information. The CTRNN might know exactly where the object is, how fast it's falling, at which angle. It might know when that object is going to hit, at which position. We can't distinguish between these two types of knowing just from how the robot is behaving, but it seems to be doing a pretty good job.
It'd be interesting to redo this, but have the objects falling in 3D, so it has to know more of where it's going to be when it loses society.
Okay, you got the spirit of the minimal cognition experiments, right? This is an extremely stripped down experiment. So for most of us, you're kind of itching to add stuff in, like let's redo it in 3D, let's drop 3 objects and see how it does. You can imagine now a series of dials in which you can gradually dial up the complexity of the task and leave maybe most of the rest of the experimental design in place.
It's kind of the same question. I was gonna ask if you could slow down pull the sensors less often, and then if it moves really fast, you know that it knew where the thing was. If it moves slowly, then...
Love it. I love it. So we could alter the experimental design to try and answer the question, how much information does the agent have at a given moment in time? Yep. Excellent. Okay. Again, very simplistic, very abstract, but going back to a practical example of an autonomous vehicle, it's driving around, there's a bunch of leaves blowing across the road, there's the traffic lights that are approaching, there's the traffic lights that are beyond the current traffic lights, there's a human over here who can't seem to make up their mind about whether they're going to try and use the crosswalk or not, there's a cloud scudding across the sun, there's a whole bunch of different things going on from the autonomous vehicle's perspective, and it needs to select to attend to some of those things. Which are the things that are relevant to whether I hit the gas or the brakes over the next 1/10 of a second? Not an easy thing to do. Depending on how we train the neural network controlling that car, it's doing it implicitly or possibly explicitly. Okay, sorry, bit of a tangent. All right, trial number 4, let's make things harder on the agent. Now, the trapezoids are going to gradually stop overlapping. We're going to have the object permanence problem and the passing objects problem. So the darker object here is initially further away, the lighter object is initially further away but is going to hit first. The darker object is closer but hits afterwards. And the agent cannot, by definition, keep both objects in sight at the same time during this time frame, this time window. What does the agent do in this case?
It shifts over to the other side to try and catch the object.
Which it does, catches the object, and then heads over and manages to catch the second object just in time. So your idea about limiting the sensors was a good one. It's acting as if it's showing us that it knows exactly where and when the second object is going to hit, even though it can't currently see it at this time, and manages to get there just in time. So it's kind of showing off again by not overly exerting itself. No efforting. Looks like. Who knows? Okay. 5th trial, same thing. We have the passing objects problem and the object permanence problem, but this one's more difficult. Why? Why is this trial more difficult than this trial?
They don't start overlapping. They start like apart.
They actually overlap, or at least the agent can be in a position in which it sees both objects for a very, very brief period of time, and then it has to select which of the two to go chase after and attend to. How does the agent do in this case? It really looks like it's hustling in this case. It's between them and almost immediately heads for this one. So it looks like it's quote unquote making a decision very quickly, because it's kind of being forced to. Not necessarily. It could go look at object 1, then go over and look at object 2, go back and look at object 1, object 2. But it doesn't seem to be doing that. It seems to be making a determination about which one is going to hit first, and almost immediately goes chasing after it and catches it with plenty of time, and then seems to be doing the same trick it did before. It heads over and catches the second object just when that object hits the ground. Okay, not the most complicated agent, but not bad. This is a non-trivial problem. Okay, any questions about that before we move on? Yes?
So So it's kind of about that, but more CTRNNs as a whole. Does gradient descent work on CTRNNs?
Does gradient descent work on CTRNNs? Gradient descent requires, when it moves backwards, that everything that happened in the forward pass is differentiable, which we'll get to in lecture 22. So, yes or no? Yes, because? What is it about CTRNNs that allows the backward pass to work?
The activation functions are different.
The activation functions inside the ordinary differential equations are differentiable. The equations themselves are differentiable. Check. You can arm a robot with a CTRNN inside a differentiable simulator, and if you do it correctly, gradient descent will be able to correctly fiddle with the body and brain in a way that guarantees the next forward pass will reduce behavioral loss, will make the robot behave more like you want it to behave. Yep. Other questions before we move on? Fitz.
It seems like they're all solvable in this. I mean, I know we didn't see all of them, and I guess I'm wondering if that is the case and what the importance of that is. Like, if you included in the batch of things that the population is learning on a
Yep.
couple of these objects where it is, even if you were to move at the optimal way, you would
Yep.
not possibly be able to catch both of them.
Great question. What's that test from Star Trek? There's a test where there is no right answer. You cannot win, and they want to see what you do with guaranteed failure. So, good point. You could easily drop both objects, so there's no way this agent, with whatever its top speed is and the rate of its sensor refreshes, that it could solve the task. Remember, ultimately, these are serving as physical Turing tests. What would you expect an agent that's good at selective attention to do under conditions where it cannot selectively attend appropriately to everything that's going on? What should it do?
Oh, and I'm kind of wondering if we know that it's actually not doing this. Is it just picking one and committing to it? Does it actually know that this object is the correct passing object? Or we just...
Who knows? We're inferring from behavior, right? Turing said we can't define intelligence, we can't define it now knows, it decides. Tricky to do. We only have the behavior, the physical movement of the robot to go on. If you saw a robot or an animal or a human trying to do this task under conditions where, let's take a human, the human can't run fast enough back and forth along the bottom of the screen to successfully catch both objects, what would you expect an intelligent human to do under those conditions?
At least try to catch them.
At least try, right? Sit down and give up? I guess it depends. Maybe that's a wise thing to do. You expect it to quote unquote try. What would try mean under these conditions? Remember, we're just looking at the movement of the robot. I guess not try would be obvious. It just doesn't move.
Catch one of them and determine which one's most likely to be caught.
Maybe. So you see an agent that just goes and catches one and acts as if it's completely forgotten about or ignored the second one. Is that the intelligent thing to do? Would there be a smarter thing to do?
After you catch the first one, keep moving to catch the other one, even if you don't catch it.
Possibly. Yeah. So I might want to show you that I know that I can't catch both. I might move in such a way where I'm showing you, I know it's going to land over there at this time. Look at my trajectory. It's literally pointing at where it's going to hit. I'm just showing you that I know, and I know that I can't get there. And now I'm going to head towards, I'm deliberately not going to catch this one, and I'm going to move in such a way that the slope of my trajectory is going to point to exactly where and when the other object is going to hit. Arguably the most intelligent thing you can do in the face of an impossible task is signal to the observer, whoever's watching, that you know it's impossible. Someone who's less intelligent might not know that it's impossible. They go and grab one object and then watch the other object hit. Yeah? Again, it's kind of subjective here, but there's different ways that an agent or a human can act to signal intelligence. I know that you know that I don't know that. Comment?
I can speak afterwards.
I'm done.
I was looking at first one where it catches one while the other object's out of view. It can move over, and then there's still time to be under it to catch it. I was thinking of if you wanted to see if it actually knows the trajectory, you could change the reward function so that it gets a higher reward for catching closer to the last second.
Absolutely, right? So the fitness function here is only rewarding CTRNs that are there when it hits. You could change it to reward for being as close as possible for as long as possible. And then it would be interesting to see whether you get trajectories like this at the end or something different. Okay, super minimal, but we're already having an interesting conversation about the nature of intelligent action. That's the point of the minimal cognition experiments. It avoids us having to define what intelligence is, decision-making, memory, prospection. That's all thrown away, and it's forcing us to conclude or make observations or change experimental design based on what the agent does. I don't know what's going on inside your head. I've never directly seen your brain. I can only assess whether or not you're acting intelligently, whether you are intelligent by observing your actions. Okay. All right, let's move on to lecture 10. The robot we're going to see in this lecture is definitely not minimal, but it's tackling a fifth sort of basic building block of intelligence. Before I introduce that building block, let me motivate it with the following hypothetical example. Let's imagine that I blindfold you. You're still sitting at the desk here, and I place one of these 11 objects on the desk. You're blindfolded, and I ask you to reach out with your hand, find the object, pat downwards towards the top of the desk until you find the object. And then I want you to tell me which of the objects that I place in front of you are round or edged. I'm asking you to classify the objects. Two classes, round or edged. It seems like an impossible question because with the blindfold off, you can see that there's a continuous gradient from round to edged. There are no two classes, two buckets. But what happens if you start to push on these objects while you're blindfolded? What happens?
Some will roll more than others.
Some will roll more than others. Depending on the texture on the top of your desk, some will roll and then suddenly they will stop rolling. If we put felt on top of the desk here, that classification boundary might be here. If we leave it smooth, it might be that all of these objects roll, but this one doesn't. There's still two categories. Those categories don't exist in the objects. These objects have been deliberately designed to show that there is no clear boundary between round and edged objects. But when you interact with them, remember our discussion about embodied cognition, categories start to emerge through the interaction. So a big part of us being able to act intelligently in the world and survive is being able to categorize between friend and foe, food and poison, and so on. But where are those categories? They're not out there in the world. They're not just in our heads. They're in our physical interaction with the objects. Embodied cognition is predicated on the idea that the body actually facilitates or helps with the acquisition of intelligent action. This is one of those examples. It's important to understand categories that are relative to us, and those categories naturally can emerge from the way we interact with those objects. If you're still blindfolded and you choose a particular action, which is just to place your hand on top of the object, but not push it back and forth, you're going to feel more or less pointiness pushing back up into your palm. That particular action of just resting your hand on top of the object, now categories don't emerge. So depending on how you interact with the objects in your world, different kinds of categories can emerge. You can choose how to act or interact with objects in the world so that categories that matter to you like the difference between food and poison, become obvious from simple tasks like lick something before you eat it.
For something like this, would you like create a fitness function that takes in the spectrum of values, and if you put alpha equals 0.1 in a square bucket, then you would end up getting a loss of 0.1 versus a gain of 0.9 or whatever?
We could do
Or
that.
would you discretize it into 10 or 11 buckets?
We meaning the investigators, right, from outside,
Mhm.
from outside the robot, we could say, here, we're deciding these are round and these are edged. So we could impose a category boundary and then train or evolve a robot to recognize the category that we think is important. Alternatively, the robot or the organism, through interactions, could come up with its own boundaries that are relevant to it. Both approaches make sense. For our purposes at the moment, what I want you to take away is the magic of the body, the magic of interaction. Categories sort of pop out where they don't exist on their own. They don't exist just in the objects, and they don't exist just in the agent's head. Okay. So how do we do this? I mentioned you spent a lot of time learning to do this when you were a kid. It's known in psychology as active categorical perception. So perception, sensing that some of these objects are rollable and some are not. Active, meaning we're not sitting at a distance and looking at the object from a distance. We're actively perceiving. We act on the world and perceive the sensory repercussions. I mentioned this at the beginning of the course. From our perspective, it's more comfortable to talk about sense, think, act. Sense, think, act, sense, think, act. But you can also go the other way. Act and observe the repercussions of your actions. Yeah? That's what the active and active categorical perception means. As human adults, most of the time you sit quietly and you learn about your world through your visual sensors, and there's not much of an outward sign that you're doing much. That's passive distal perception. That's what you do most of the time. When you were a kid, first of all, your eyes weren't when you were very, very young, your eyes didn't provide a lot of visual information. Everything was kind of blurry. You learned mostly about the world through active categorical perception. And as you got better at doing that, learning about the world, what you learn through active categorical perception becomes a scaffold on which you got better and better at distal passive perception. Now you do it so much, you might not even realize that you did so. There are some hints remaining in most human languages for this fact. When you're in math class, when you're grappling with an equation, or you expand it, or you contract it, when you rotate three-dimensional objects in your head, you're rotating them, you're twisting them, you're manipulating. Manipulating literally means with your hands. When we describe abstract things that we do in our heads, we often seem to use language that has to do with manipulation, actively grappling with things in the world. Okay, so active categorical perception is an important building block of intelligence, but for most human adults, we sort of overlook it because we don't really use it much anymore. It's like training wheels on a bike that we threw away a long time ago. Okay, let's dig down into active categorical perception a little bit more. What does it mean to interact with the world such that good categories emerge for us? For example, distinguishing between food and poison. Distinguishing between green and red fruits, you could do it, but maybe that's less relevant of a category than food or poison. That category, those categories and the distinction between them, that matters much more for us than green versus red. So how do you interact with things to get the good categories to emerge? You need to choose how to act, You need to choose how to interact so that you reduce within category differences. I ate this green thing and I was poisoned so bad I couldn't do anything else for 3 days. And then I also ate this other red thing and also got slightly poisoned and couldn't do thing for 3 days. So I'm going to reduce my reliance on the color of fruit. That's not so relevant, I'm learning to my detriment, is important for me. I start licking various types of fruit and they're either super bitter or super sweet. And I'm going to sort of interact with, take a nibble on that so I can tell the bitterness or the sweetness of that fruit. I'm going to interact or bite on that object in different ways to magnify that difference. This is a little bit bitter, maybe it's a little bit sweet. Let me take a slightly bigger bite. So when we do ACP well, we're learning which way to interact with objects in the world to do two things. Reduce unimportant within category differences and magnify important between category differences. A robot or a human or an animal that can't do this very well, it's going to get just sick quite often. Yeah, very important. Okay, so in the experiment we're going to talk about over the next 20 minutes or so is going to evolve a robot to do this well, to do ACP well. This robot is going to be armed with a CTRN, as we've seen before, but you can see that it's obviously not a minimal robot. It's actually quite a complex robot, and it's an anthropomorphic robot. Anthro meaning human, and pomorphic meaning in the shape of. So they built, in this case, a lot of human physiology into this robot, and they left some out, such as the fact that this robot is just an arm. Okay, so let's go through the task first. You can see the arm and the hand here. They're going to, as we saw before in the minimal cognition experiments, they're going to evolve a population of CTRNs, and they're going to evaluate each CTRN. They're going to drop that CTRN into the robot 16 times. They're going to put the robot's initial arm to this angle. This is called position A. And then they're going to place one of these 8 objects underneath the robot's palm. The robot is going to interact with that object, and they're going to compute how well the robot does at ACP for that object. We'll get to that in a moment. They put the robot's arm back to position A, chose another one of these 8 objects, put it underneath the robot's arm, repeat 6 more times. We've evaluated one CTRN 8 times. Now put the robot's initial position, put the robot's arm into position B, and then do the same thing. Randomly put each of these 8 objects underneath the robot's arm. Obviously, as you can see, they're not actually 8 objects. There's just 2 different objects. And the second one is rotated horizontally at a different angle underneath the robot's palm. So imagine, again, you're blindfolded, and I tell you that I'm going to evaluate your performance 16 times. I move your arm here, and then I put some object underneath, and you do something. You interact with that object in some way, and I'm going to evaluate your performance. As was mentioned earlier in the lecture, you don't know what your goal is. You're not told what it is you're supposed to be doing. You just do something. In the case of the robot, it's being controlled by a CTRN with some set of parameters, which we'll get to in a moment. So far, so good? Okay. Let's look at the robot's anatomy. This might be a little bit difficult to see here, but if we walk from the shoulder down to the wrist, we see J1, J2, 2 rotational joints, J1 and J2 in the shoulder. There's a 3rd joint in the upper arm, which is meant to approximate this. J4 does this. J5 does this, and J6 does this, and J7 does this. So they're getting the mechanical degrees of freedom, the rotational degrees of freedom, more or less right in the arm. And then in the hand, they got a whole bunch of mechanical degrees of freedom, like you also have. Part of the reason why we've done so well on this planet, at least so far, is because of what we can do with our hands. Okay, so we've got all of these blue cylinders. These represent hinge joints. So there's 1, 2, 3, 6, 9, 12, 15 rotational joints in the hand. Okay. We'll notice that there are also some blue circles here. These represent sensors, either touch sensors, something's pressing against the palm or the underside of a finger, or they represent proprioceptive sensors, the angle of different joints in the arm or the hand. So far, so good? Okay. That's the body of the robot. Let's have a look at its brain. This is a visual representation of a CTRNN, and the mathematical description is down here. I like this figure from this paper. It helps you build up an intuition for how CTRNNs work. We can jump back and forth between the visual and the mathematical representation. Let's start with the visual representation. There are 7 neurons inside the CTRNN attached to the 7 joints in the arm. 1, 2, 3, 4, 5, 6, 7. So these 7 neurons are reporting the angle of those joints in the arm as the robot moves. There are an additional 10 neurons assigned to the touch sensors in the finger, represented by the 10 circles in the hand here. The underside of your hand, obviously, you can tell a lot of detail, shape detail on the underside of your hand. On the back of your hand, much less. Why? You don't grab things with the back of your hand. You can't grab things with the back of your hand. A lot of tactile information clustered on the underside of your hand. That's what they're capturing here in the CTRNN. And then we have an additional 5 neurons that are reporting proprioceptive information. The 5 represent the overall angle of each of the 5 fingers. Why not 15 proprioceptive sensors? A little bit of human anatomy this morning. Why only 5? Why aren't they reporting the angle of what's called the proximal, middle, and distal phalanges? You've got 3 parts to your fingers. Each of them can rotate. Why only 5?
Because the distal joint kind of produces the largest range of motion, so it's kind of like the majority of what you need in that one.
Kind of. These 5 are reporting the overall curvature of the finger, the flexion of the finger, how much the finger is being flexed or extended, not the individual flexion and extension of each of the 3 phalanges in each of your fingers. Why not? You kind of throw that detail away.
You kind of get the information of the rest. You've got like an approximation of it, and it's simpler, so it's going to be easier to process.
The overall curvature of your finger correlates with the rotation of each of your phalanges, because most of us can't rotate our phalanges independently. There's a small fraction of us that can. It's kind of a party trick. But most of the time, if you want to flex the upper part of your finger, you also kind of flex the lower part of your finger. Kind of. So they're kind of simplifying things a little bit. I think these investigators just had fun throwing in a whole bunch of human physiology to this robot. Okay, so we've got a total of 22 neurons that are receiving sensory information from the arm and the hand. Those 22 neurons connect to a bunch of internal neurons. How many do we have here? 8 internal neurons or hidden neurons. Internal and hidden neurons mean the same thing. And then these 8 internal neurons connect to a whole bunch of motor neurons. There are 14 motor neurons for the arm, but remember that there were only 7 joints. Why 14 motor neurons for 7 joints? Should only need 7 motor neurons for the 7 joints.
Like a push and a pull.
a push and a pull. So they're capturing another detail of human physiology, is that for most of the major body parts in your body, you have pairs of muscles which are agonist and antagonist muscle groups. So think about your bicep and your tricep. If you want to flex your arm, you contract your bicep and you relax your tricep. If you want to extend your arm, you compress your tricep and you relax your bicep. For whatever reason, Mother Nature decided it was good for us to be able to do this, but these are controlled by ropes, your muscles, and ropes can pull, but ropes cannot push. So Mother Nature solved this problem by attaching pairs of opposing ropes to most of your major body parts, like your lower arm attached to your upper arm to allow for this. So they assigned 2 motor neurons to each rotational joint, and they took the difference between them to pull and to push. They didn't have to. As you're doing in the assignments, it's perfectly fine to have 1 motor neuron where the negative number represents flexion and the positive number represents extension. I always get that wrong. Doesn't matter. That's why they've got 14. They're trying to capture another physiological detail. There are only 2 motor neurons assigned to the hand. It's again antagonistic and it's an antagonistic and agonist muscle group. When 45 fires strongly, it causes forces for the joints to open the hand. When 46 fires strongly, that sends forces that cause the joints to contract and close the hand. If both 45 and 46 are firing strongly, you have a rigid hand. If 45 and 46 are firing with values near 0, you've got a ragdoll hand. So far, so good? Okay. In the interest of time, I will leave it to you to take this visual representation and match it to the mathematical description. I want to focus now on the 47th and 48th neuron inside the 48 neuron CTRNN that controls this robot. These 2 neurons are responsible for active categorical perception, as we'll see in a moment. Okay, we're going to evolve all of the coefficients that make up these 48 ordinary differential equations. We're going to evolve them against a fitness function that rewards CTRNNs that can tell us when the hand is in the presence of a sphere and when the hand is in the presence of an ellipsoid. So as was pointed out earlier, we're kind of cheating a little bit. We are giving the categories to the robot. We are going to evolve a robot so that it can distinguish between or categorize between objects that are important to us. We want, for whatever reason, we want this robot to tell the difference between spheres and ellipsoids, which you can do very quickly from a distance passively by looking at them. It's easy for you. For a little human child or a robot that's blind, it has to grab the object and play with it to tell whether it's a sphere or an ellipsoid. You can see that they picked the major and minor axes of these ellipsoids to make this ellipsoid quite close to a sphere. Again, for you, maybe you could easily tell the difference. Not so easy for the robot. So when we put a sphere underneath the robot's hand, we want the CTRNN to say sphere. When we place an ellipsoid underneath the robot's hand, we want the CTRNN to say ellipsoid. If it says the wrong thing, that CTRNN's fitness is going to be lower than another CTRNN that says the right thing more often. So far, so good? Okay. What do you think 47 and 48 represent? Remember, at every time step, we're going to propagate values from the input layer to the hidden layer to the output layer. So at every time step of the simulation, there are going to be floating point values inside neuron 47 and 48.
Binary representation of like round or edge.
Okay, binary representation. Maybe we're going to evolve the weights so that when a sphere is placed underneath the robot's hand, 47 goes to 1 and 48 drives towards 0. When we place an ellipsoid underneath the robot's hand, 47 should go to 0 and 48 should go to 1. Yeah? Okay, a good idea, but if we then started to... Question?
I had an idea about it.
Okay, let's go with this idea. We could do that. We could evolve. We can create a fitness function that rewards for that. If we then start to put cubes underneath the robot's hand, we got to add neuron 49. If we then start to put cylinders under the robot's hand as well, we got to add neuron 50. If we add trapezoids, now we've got to add another neuron, a new category, new neuron, new category, new neuron, new category, new neuron. We've talked about this before. It's a simple solution, but it's problematic because it doesn't scale very well. Or we need to make the architecture, the cognitive architecture of the CTRN bigger and bigger and bigger.
For most like categorization like tasks that I've done in machine learning, like it is that where it's one uncoded like
Yep.
probabilities. Would this be less of that and more features where it's maybe level of roundness or axes, like the diameters or amounts of the ellipsoids and stuff?
It could be. Maybe we're going to use these two neurons to evolve such that they report features of the objects rather than it is a sphere or an ellipsoid. You mentioned this idea of this binary categorization. This is what people do in machine learning. It's because they're slackers. It's lazy, and it's a simple way to do things. It's not a good way to do things because, again, we have to keep adding more neurons. And the CEO of NVIDIA wraps his hands and says, great, I'm going to be able to sell you more GPUs. Good. Keep making things bigger and more computationally expensive, more carbon, more money, bad, bad, bad. Mother Nature does not do things like that. Yeah? So let's try in this experiment, the reason we're talking about it, aside from ACP, is the investigators did neither of what the two of you suggested. They did something else. So that if they were to redo this experiment and now expose the robot to cubes, you wouldn't have to add any new neurons. We've only got a few minutes left, so I'm just going to start in on what I think is an ingenious solution to this problem. Let's imagine a robot, this robot armed with a random CTRN, and we're going to plot the value of the 47th neuron, and we're going to plot the value of the 48th neuron as the simulation starts running. Let's assume 0 is here and 0 is here, and let's assume that at t equals 0, at the beginning of the simulation, the two values at 47 and 48 are 0. At the next time step, sensor values have flowed through to these neurons, and they now take on some new values. Let's say these two values, this value of 47 and this value of 48. At t equals 1, the next time step. At the next time step, the two neurons have this value, then this value, then this value, then this value, then this. And by drawing it in this way, we can visualize how neurons 47 and 48 are changing over time. Remember, they're changing continuously because this is a CTRNN. What we've just drawn here is what's known as a phase diagram. Let's assume that the robot traced this trajectory, or the neurons traced this trajectory when the robot was in the presence of a sphere. We put the arm back to position A, we reset the robot, we keep the same random CTRNN inside the robot, and now we slip an ellipsoid underneath its palm. It doesn't know that the object has changed, but we start the simulation again, and again the neurons start at 0, 0, but now in the presence of a different object, which generates a different perception, which causes the hidden neurons to have new values, which causes 47 and 48 to have different values, we get a different trajectory. This is the trajectory that's produced by the robot when it's in the presence of the ellipsoid.
This doesn't like actually categorize it though. It just you would then need to throw it into a new clustering algorithm to do that.
Exactly. We haven't even got to categorization yet. We've just exposed the robot to two different environments, and the robot moves differently or acts differently, and these neurons just assume these different values. We haven't done any categorization yet. Question?
Yeah, so in the context of like a one hot encoded output layer, all of the resulting vectors would be orthogonal. So wouldn't that, in the context of active categorical perception, work to magnify the between category differences?
Yes, it would magnify it because we're asking 47 and 48 to have very different values in the presence of the sphere and the ellipsoid. So yes, it's magnifying between category differences, but at a cost. More neurons for more categories, which means more compute, more energy, more carbon. And in the case of humans, maybe more neurons in the skull, which means a bigger skull, which means greater maternal or child death during birth. So for our particular species, there was and is, or at least was, a very, very strong cost against making bigger brains. We have big brains for a very good reason, but Mother Nature, presumably, especially in us, wanted to make the best use of neural real estate that she could. And in this experiment, which will continue next time, you're going to see how the investigators made good use of neural real estate. Let's put a pin in things here for today. You've got a quiz due tonight. You're working on A6 or D1. See you on Thursday.